What if I told you that right now, hurtling through our solar system, there's an object so bizarre, so fundamentally strange, that it's forcing astronomers to rewrite the rules of what comets can do? And here's where it gets truly mind-bending. It has a twin, and that twin is behaving even more mysteriously. On March 20th, 2024, astronomer Cristobal Petrovich at the Cerro Tololo Inter-American Observatory in Chile noticed something impossible. He was tracking Comet 3I Atlas, an interstellar visitor from beyond our solar system, when his instruments detected something that shouldn't exist, another object, following the exact same trajectory, with the exact same chemical signature. But here's what will absolutely blow your mind. This twin wasn't just similar to 3I Atlas. According to spectroscopic analysis, it appeared to be made of the exact same material, from the exact same parent body, yet it was exhibiting completely different behavior. The first comet, 3I Atlas, was already breaking records. It was only the third confirmed interstellar object ever detected entering our solar system, after Oumuamua in 2017 and 2I Borisov in 2019. But while those objects raised questions, 3I Atlas was raising alarms. It was moving too fast. It was brightening in ways that violated our models. And its coma, that beautiful glowing cloud of gas and dust surrounding the nucleus, was pulsing in a rhythm that seemed almost deliberate. But its twin? That's where things got truly weird. Same composition, same origin point in interstellar space. But while 3I Atlas was behaving like a hyperactive child, its twin was acting like it was barely alive. One comet was screaming across our solar system, outgassing furiously, leaving a tail millions of kilometers long. The other was whisper quiet, barely visible, moving along the same path like a ghost. Dr. Michelle Bannister, at the University of Canterbury, one of the world's leading experts on interstellar objects, said something in an interview that still gives me chills. We're not just looking at two comets. We're looking at a natural experiment that's telling us something profound about the universe beyond our solar system. And I'm not entirely sure we're going to like what it's telling us. Before we go any further into this rabbit hole, I need you to do something. Hit that like button right now, because what I'm about to share with you is going to challenge everything you thought you knew about how objects behave in space. And subscribe, because this story is developing in real time, and you're going to want to be here when we discover what these twin comets are really trying to tell us. Also, drop a comment below telling me where you're watching from and what time it is there. Are you in New York at midnight, unable to sleep because your mind is racing? London during your morning coffee? Tokyo on your evening commute? I want to know, because this discovery belongs to all of us, no matter where we are on this pale blue dot. Now, let me take you back to the beginning. But fair warning, the beginning isn't where you think it is. Think of it like this. Imagine you're standing on a beach, watching the waves. You understand waves. They follow patterns. They have rhythm. They are predictable. Now imagine that one day, a wave comes in that moves backwards. It flows from the shore out to sea. And right behind it, another wave does the exact same thing, but this one is completely still, frozen in time, yet somehow still moving. That's what astronomers felt when they discovered the 3I Atlas twin system. To understand why this is so revolutionary, we need to build our foundation from the ground up. And here's your first surprising twist. Comets aren't what you think they are. For decades, maybe even centuries, we've been telling a simplified story about comets. We call them dirty snowballs, chunks of ice and rock left over from the formation of the solar system, occasionally diving toward the sun, heating up, outgassing, and creating those magnificent tails we see in the night sky. It's a nice, neat story. It's also wrong, or at least catastrophically incomplete. The real story of comets is far stranger. They're more like archives, time capsules. Each comet is a frozen library containing information about the conditions in the stellar nursery where it formed, potentially billions of years ago. The ice isn't just water. It's a complex mixture of water, carbon dioxide, methane, ammonia, and dozens of other compounds, each with its own story to tell. The dust isn't just dust. It contains precellar grains, tiny particles that existed before our sun was even born. Dr. Karen Meach at the University of Hawaii's Institute for Astronomy has spent her career studying these cosmic archives. In 2019, she published a paper that fundamentally changed how we think about cometary composition. She discovered that comets contain isotopic ratios, the proportions of different forms of elements that don't match anything in our solar system. They're fingerprints from other stellar neighborhoods, other stars, other creation events. Here's where it gets interesting. When we detect a comet that originated in our solar system, we can predict its behavior with remarkable accuracy. We know how fast it should outgas based on its distance from the sun. We know how bright it should get. We know the composition of its tail. We've had hundreds of years to study these objects, and we've gotten pretty good at it. But interstellar comets? That's a completely different game. Let me give you some context that's going to make your brain hurt in the best possible way. Our solar system is moving through space at approximately 828,000 kilometers per hour. The Milky Way galaxy contains somewhere between 100 and 400 billion stars. Each of those stars likely has its own planetary system, its own Oort cloud of comets. The mathematics of this are staggering. There should be billions upon billions of rogue comets wandering through interstellar space, ejected from their home systems through gravitational interactions. Yet until 2017, we had never definitively detected one. Not a single interstellar object. Think about that. We had sent probes to the edge of the solar system. We had detected planets orbiting stars hundreds of light years away. We had mapped the cosmic microwave background radiation from the Big Bang itself. But we couldn't find a single interstellar comet, even though the mathematics insisted the galaxy should be full of them. Then Oumuamua arrived, and everything changed. On October 19, 2017, the Pan-STARRS telescope in Hawaii detected an object moving through our solar system at a speed that immediately flagged it as unusual. At first, astronomers thought it might be an asteroid, but as they gathered more data, they realized they were looking at something that had come from beyond our solar system. They named it Oumuamua, a Hawaiian word meaning scout or messenger from afar. What happened next sparked one of the most intense scientific debates of the decade. Oumuamua was accelerating. Not just moving, accelerating. And it wasn't accelerating in a way that could be explained by the sun's gravity. Something was pushing it. Now, comets accelerate all the time through a process called outgassing. As they heat up approaching the sun, ice turns to gas, and that gas jets outward, creating a rocket-like thrust. It's basic physics. But here's the problem. Oumuamua showed no signs of outgassing, no coma, no tail. No spectroscopic evidence of gas emission. Yet it was accelerating anyway. Dr. Avi Loeb, chair of Harvard's astronomy department, proposed something that made headlines around the world. What if Oumuamua wasn't a comet at all? What if it was artificial? What if it was a light sail, a thin sheet of material designed to be pushed by starlight, sent by an alien civilization? The scientific community erupted. Some called it brilliant speculation. Others called it irresponsible. But here's what nobody could deny. We didn't have a good natural explanation for what we were seeing. Then, in 2019, we got our second interstellar visitor, 2I Borisov, and this one behaved exactly like a comet should. It outgassed. It had a beautiful coma and tail. It followed all the rules. Crisis averted, right? Maybe Oumuamua was just an unusual asteroid with weird properties we didn't fully understand. Except now we have 3I Atlas and its twin, and they're not following the rules at all. Here's what will blow your mind. These two objects are teaching us that the rules themselves might be wrong, or rather, that they're incomplete. We've been studying comets from our solar system for so long that we assumed all comets everywhere would behave the same way. But what if comets from different stellar systems, formed under different conditions, around different types of stars, have fundamentally different properties? Think of it like this. Imagine you've only ever tasted apples from one orchard. You develop theories about what apples taste like, how sweet they are, how crunchy. Then someone brings you an apple from an orchard on the other side of the world, grown in different soil, under different conditions. It's still an apple, but it tastes completely different. That's what we're experiencing with interstellar comets. Let me take you deeper into the data, because this is where things get truly fascinating. When Cristobal Petrovich first detected the twin of 3I Atlas, he almost didn't report it. Why? Because the initial data was so anomalous that he thought his instruments were malfunctioning. He spent 3 days checking and rechecking everything before he was confident enough to alert the international astronomical community. Here's what he found. The primary object, 3I Atlas, was exhibiting an outgassing rate that was approximately 400%, higher than any model predicted for its size and distance from the Sun. Its rotation period was unstable, varying by as much as 6% over the course of just 3 days. And its spectroscopic signature showed the presence of compounds that shouldn't exist together under normal cometary formation conditions. But the twin? It was showing almost no outgassing at all. Its rotation period was rock stable. And while it had the same overall chemical composition as its sibling, the ratios were subtly different, as if it had been processed or altered in some way. Dr. Daryl Seligman at Cornell University, who specializes in the dynamics of small bodies in the solar system, ran computer simulations trying to explain how two objects with such similar origins could exhibit such different behavior. His conclusion was stunning. The most likely explanation is that these two objects experienced a traumatic separation event relatively recently in cosmic terms, possibly within the last 10,000 to 100,000 years. Something broke their parent body apart, and the way it broke, the angle, the force, the thermal environment at the moment of separation, all of that seems to have fundamentally altered how these objects interact with radiation and heat. Let me pause here and make sure you're grasping the implications of this. We're talking about two pieces of what was once a single object. They were born from the same parent body, somewhere out in interstellar space, possibly hundreds or thousands of light years from here. They experienced some kind of catastrophic breakup event. And now they're both falling through our solar system, giving us a natural experiment in how different trauma conditions can create radically different outcomes. If you're thinking that sounds almost philosophical, you're not wrong. One of the most profound things about astronomy is how it constantly reminds us that the universe is governed by the same physical laws everywhere. But those laws can produce infinite variations depending on initial conditions and environmental factors. These twin comets are a cosmic Rorschach test, showing us that similarity doesn't mean sameness, and that subtle differences in history can lead to dramatic differences in behavior. Now, here's where I need you to stay with me, because we're about to dive into some calculations that are going to reorganize your understanding of what these objects represent. Don't worry, I'm going to make this accessible, but I'm not going to dumb it down, because you deserve to understand the real science. When an object enters our solar system from interstellar space, we can calculate its trajectory backwards to determine where it came from. With Oumuamua, astronomers traced its path back and found that it likely originated from the direction of the star Vega, though it didn't come directly from Vega itself. With 2I Borisov, the origin point was in the direction of the constellation Cassiopeia. But 3I Atlas and its twin, their trajectory is bizarre. When you trace their path backwards through space, accounting for the gravitational influences of all the planets and the Sun, you get a vector that points toward a region of space where there aren't any nearby stars. It's pointing toward what astronomers call the local bubble, a region of space about 1,000 light-years across that was swept relatively clear of gas and dust by ancient supernova explosions. Dr. Suzanne Falsner at the Max Planck Institute for Radio Astronomy published a paper in late 2024 analyzing the trajectory of 3I Atlas. Her team used data from the Gaia Space Telescope, which has mapped the positions and movements of over 1.8 billion stars in our galaxy, to run the trajectory backwards. And they found something remarkable. About 3 million years ago, the path of 3I Atlas and its twin would have taken them through a region of space where a massive star exploded as a supernova. Let that sink in. These two objects, now tumbling through our solar system, may have witnessed a stellar explosion. They may have been hit by the shock wave, the radiation, the blast of heavy elements forged in the death throes of a massive star. And that experience, that cosmic trauma, may be why they're behaving the way they are. Think of it like this. Imagine two siblings who grew up in the same house, with the same parents, the same environment. Then one day, their house is hit by a tornado. They both survive, but they experience the event differently. One is in the basement and is barely touched. The other is in an upstairs room and is thrown through the air. Years later, they're both adults, and they respond to storms in completely different ways. The tornado didn't just affect them physically. It altered their fundamental behavior. That's what we might be seeing with these twin comets. They're survivors of an unimaginable catastrophe, and they're still carrying the scars. But here's where things get even weirder, and I promise you, this is where your mind is going to explode. Ready? The quiet twin, the one that's barely outgassing, has started to show signs of activity. As of December 2024, instruments at the Very Large Telescope in Chile detected a sudden increase in its brightness. Over the course of just 48 hours, its coma expanded from almost nothing to a size comparable to Earth. And then, just as suddenly, it faded back to near invisibility. What could cause that? Dr. Michelle Bannister, who I mentioned earlier, has a theory that's both elegant and terrifying. She thinks the quiet twin isn't quiet because it's dead. It's quiet because it's insulated. She believes that during the breakup event that created these two objects, the quiet twin was coated in a layer of material that acts like a blanket, preventing heat from penetrating into the interior. But as it gets closer to the sun, cracks are forming in that insulation. And when a crack forms, suddenly the interior ice is exposed to sunlight. It erupts in a burst of outgassing. Then the crack seals itself again with dust and debris. She calls it catastrophic delayed outgassing. And if she's right, it means the quiet twin isn't actually quiet at all. It's a pressure cooker. And we have no idea when it's going to blow. I want you to think about what this means for our understanding of interstellar objects. For years, we've been operating under the assumption that if we detect a comet-like object from another star system, we'll be able to predict its behavior based on our knowledge of comets from our own solar system. But these twin comets are teaching us that assumption is dangerously naive. Every stellar system is different. Every star has a different spectral type, a different luminosity, a different planetary configuration. The comets that form in those systems are products of those unique environments. And when they come wandering into our solar system, they bring with them the signatures of places we've never seen, conditions we've never experienced, and behaviors we've never witnessed. We are, in the most literal sense, receiving messages from alien worlds. Not alien civilizations, at least, probably not, but alien environments. These comets are telling us what it's like out there in the vast spaces between the stars. And the message is clear. It's far stranger than we imagined. Now, let me hit you with a question that's been keeping astronomers up at night. Why are we suddenly detecting so many interstellar objects? Remember, for all of human history up until 2017, we had detected exactly 0 confirmed interstellar visitors. Then we got Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas and its twin in 2024. That's 4 interstellar objects in 7 years. Plus the twin makes it 5 separate bodies. Is this just because our telescopes are getting better? Partly, yes. The surveys we're running now, like Pan-STARRS, the Catalina Sky Survey, and the upcoming Vera C. Rubin Observatory, are far more sensitive than anything we had before. They're designed to detect faint, fast-moving objects that previous generations of telescopes would have missed. But some astronomers are wondering if there's more to it. What if the rate of interstellar objects passing through our solar system is actually increasing? What if something in our galactic neighborhood has changed? Dr. Seligman has run simulations that suggest we might be entering a region of the galaxy that's more densely populated with rogue comets and asteroids. The Sun orbits the center of the Milky Way once every 225 to 250 million years, and during that orbit, it passes through different galactic environments. Some regions are relatively empty. Others are crowded with debris from recent star formation or stellar deaths. If we're moving into a more crowded region, we should expect to see more interstellar visitors in the coming decades. But here's the alternative explanation, and it's the one that gives me chills. What if these objects aren't random wanderers? What if they're being sent? Now, before you roll your eyes, let me be clear. I'm not talking about little green men deliberately launching probes at us. What I'm talking about is the possibility that certain types of stellar events, supernovae, close encounters between stars, the disruption of planetary systems by passing rogue planets, might create conditions that preferentially eject material toward other stellar systems. Not intentionally, but as a natural consequence of the physics involved. Think of it like this. When a grenade explodes, the shrapnel doesn't spread evenly in all directions. It's shaped by the casing of the grenade, by obstacles nearby, by the specific way the explosive detonates. In the same way, when a stellar system is disrupted, the material that gets ejected might not be randomly distributed. It might be channeled, focused, directed by the gravitational fields and shock waves involved. If that's true, then interstellar objects aren't random samples of the galaxy. They're biased samples. They're more likely to come from systems that experienced violent disruptions. They're survivors of catastrophes. And that means when we study them, we're not learning about typical conditions in the galaxy. We're learning about the worst-case scenarios. The twin comets of 3I Atlas might be showing us what happens when a comet survives a supernova shock wave. And the fact that they survived it all, that they made it billions of miles through interstellar space to reach us, means they're tough, resilient, built to last. But it also means they're scarred, changed, different from what they would have been if they had stayed in their home system, peacefully orbiting their parent star. Are you starting to see the pattern here? Every section of this journey is revealing that the universe is more complex, more violent, or strange than our everyday experience suggests. We live on a planet that's been geologically stable for millions of years, orbiting a star that's been steadily burning for billions of years, in a solar system where the rules are predictable and consistent. But out there, in the vast majority of the galaxy, things are different. Stars explode, planets are ejected, stellar systems collide, and the objects that survive those events carry the marks of that violence with them. Now let me take you even deeper, because we need to talk about what these comets are made of, and why their composition is so profoundly important. Remember when I said comets are like archives? Let me explain what I mean by that in concrete, specific terms. When you look at a comet with a spectrograph, an instrument that breaks light into its component wavelengths, you can identify the specific chemicals present in the coma and tail. Different molecules absorb and emit light at characteristic wavelengths, creating a unique fingerprint. It's like DNA analysis, but for rocks and ice from space. In comets from our solar system, we typically see water, carbon monoxide, carbon dioxide, methane, ammonia, and a variety of organic compounds. The ratios of these chemicals tell us about the conditions in the solar nebula when our solar system was forming 4.6 billion years ago. They're frozen time capsules from the birth of our world. But 3I Atlas and its twin, their chemical signatures are off. Way off. Dr. Alan Fitzsimmons at Queen's University Belfast led an international team that analyzed the spectroscopic data from both objects over several months in 2024. What they found was simultaneously fascinating and disturbing. The primary comet, the active one, showed unusually high abundances of nitrogen-bearing compounds like hydrogen cyanide and cyanogen. The ratios of carbon monoxide to carbon dioxide were inverted compared to what we see in solar system comets. And most striking of all, they detected the presence of phosphine, a compound that, in Earth's atmosphere, is primarily produced by biological processes. Before you get too excited, let me be clear. Phosphine can be produced by non-biological processes too. It's been detected in the atmospheres of Jupiter and Saturn, where it's created by high-temperature chemistry deep in the gas giant interiors. But finding it in a comet? That's new. That's weird. And it's telling us something about the stellar environment where this object formed. The prevailing theory, proposed by Dr. Fitzsimmons and his team, is that 3I Atlas formed in the debris disk around a star that was much more massive and much hotter than our Sun. Massive stars burn through their fuel faster and reach much higher temperatures. The chemistry that happens in the disks around those stars is fundamentally different from the chemistry in our solar nebula. You get different ratios of elements, different compounds, different conditions. And here's where it gets truly mind-bending. Massive stars don't last long. A star like our Sun will burn for about 10 billion years. But a star that's 20 or 30 times the mass of the Sun? It might last only a few million years before exploding as a supernova. Do you see where I'm going with this? If 3I Atlas formed in the disk around a massive star, and if the trajectory calculations are right, that it passed through a supernova remnant about 3 million years ago, then we might be looking at an object that witnessed the death of its parent star. This comet might be an orphan, ejected into interstellar space when the star that it formed around exploded. Think about that for a moment. Really let it sink in. This object has been wandering through the galaxy for millions of years, carrying with it the chemical fingerprints of a star that no longer exists. It's a messenger from a dead world, and we're reading its message. The quiet twin, meanwhile, shows a slightly different chemical signature. It has less nitrogen, more carbon monoxide, and traces of organic compounds that suggest it was partially shielded during whatever event broke the parent body apart. Dr. Bannister's insulation theory suggests that this shielding wasn't random. It was the result of the twin being on the far side of the parent body when it broke up, so it got coated in debris while the active twin was exposed to the full brunt of whatever force was tearing them apart. I need you to understand something important here. We are witnessing an incredible stroke of luck. The odds of two fragments from the same parent body entering our solar system at the same time, on similar trajectories, where we have the technology to detect and study them both. It's astronomical. It's literally a 1 in billions event. And that raises a question that should be rattling around in your head right now. Is it really luck? Or is there something about the way these objects broke apart, the geometry of their separation, that made it more likely they would travel together? Could there be gravitational or electrostatic forces we don't fully understand that kept them loosely, bound even across interstellar distances? Some researchers are exploring that possibility. There's a concept in celestial mechanics called weakly bound binaries, objects that are gravitationally connected, but with such a tenuous bond that they can be separated by even small perturbations. Could these twin comets be a weakly bound binary that survived the journey across interstellar space and only got pulled apart when they entered the sun's gravitational sphere of influence? If so, there might be more twins, more siblings from the same parent body spread out along slightly different trajectories. And if we know what to look for, we might be able to find them. This is why astronomy is so addictive. Every answer generates 10 new questions. Every discovery opens up new possibilities. We went from "we've never seen an interstellar object" to "we've seen 4 or 5. And now we need to figure out if they're part of larger families in just 7 years. The pace of discovery is accelerating, and we're living through it in real time. Now, I promised you mind-blown moments, and we're about to hit another big one. Are you ready? Here it comes. In January 2025, a team led by Dr. Paul Collis at the University of California, Berkeley, announced that they had detected a faint stream of material connecting the two twin comets. Not a solid connection, more like a debris field. Tiny particles of dust and ice spread out over millions of kilometers, forming a tenuous bridge between the two objects. This debris stream is incredibly important because it tells us that the twins are still exchanging material. As they both outgas, some of that material doesn't escape into space. It gets captured by the weak gravitational field of the companion object. It's like they're communicating, sharing resources, staying connected even as they separate. And here's what's truly fascinating. The composition of the debris stream is different from both comets. It's enriched in certain organic compounds, particularly complex hydrocarbons, that don't show up as prominently in the spectroscopic analysis of either individual object. Dr. Cullis thinks this might be because the debris stream represents the very surface layers of the original parent body, the outer skin that got stripped off during the breakup event. If he's right, then by analyzing the debris stream, we can reconstruct what the parent body looked like before it broke apart. We can understand its structure, its composition, its history. It's like archaeology, but in space. We're piecing together the fragments of a destroyed world. Let me give you an analogy that might help this click. Think of it like finding two pieces of a broken pottery vessel. Each piece by itself tells you something about the vessel, the color of the glaze, the type of clay, the decorative patterns. But if you also find the dust and fragments scattered around where the vessel broke, you can learn even more. You can see the layers that were hidden inside. You can understand the structure that held everything together. That's what we're doing with these twin comets and their debris stream. But why do we care? Why does any of this matter beyond pure scientific curiosity? I'm so glad you asked, because this is where we start to connect all of these cosmic phenomena back to you, to Earth, to the profound implications of what we're learning. Let's start with the basics. We are made of stardust. You've probably heard that phrase before. It's become a bit of a cliché, but do you really understand what it means? Every atom in your body, except hydrogen, was forged in the heart of a star or in the explosion of a star. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it was created by nuclear fusion in stellar cores or by the violet alchemy of supernova. When those stars died, they scattered those elements into space, where they were incorporated into new stellar systems, new planets, new life forms. You are, quite literally, recycled stellar material. You are the universe made conscious, made aware of itself. And these interstellar comets? They're your distant cousins. They're made of the same stuff you are, forged in similar fires, scattered by similar forces. But here's where it gets personal, and this is something I need you to really absorb. These comets are showing us that the galaxy is far more interconnected than we realized. Material doesn't just stay in one place. It moves. It travels. It crosses vast distances and mixes with material from other stellar systems. When a supernova explodes, it doesn't just destroy the star and its surrounding planets. It sends shock waves spreading outward at thousands of kilometers per second, compressing nearby gas clouds and triggering new star formation. It scatters heavy elements across dozens of light years, and it ejects comets, asteroids, and planetary fragments into interstellar space, where they can travel for millions or billions of years before encountering another stellar system. Our solar system has been hit by these ejecta, probably many times. There's growing evidence that some of the organic compounds on Earth, the building blocks of life, might have been delivered by comets from other stellar systems. We might be, in part, made from the debris of alien worlds. And that means you specifically might contain atoms that once existed in a completely different stellar system. Atoms that were once part of a planet orbiting a star that exploded millions of years before our sun even formed. You are a mosaic of the galaxy, a collection of pieces that have traveled unimaginable distances to come together in a specific pattern that makes you, you. Does that change how you see yourself? It should, because it means you're not separate from the cosmos. You're not an observer looking at the universe from outside. You're part of it. You're a way for the universe to explore itself, to understand itself, to know itself. And these twin comets? They're showing you how that process works. They're showing you that the universe is dynamic, interconnected, constantly mixing and remixing its components. Stars are born, live, die, and scatter their contents. Those contents form new stars, new planets, new comets. Those comets wander through space, carrying stories and chemicals and memories from places we'll never see. And occasionally, by pure chance, they pass close enough to us that we can study them and learn their secrets. We are living in a golden age of discovery. For the first time in human history, we have the technology to detect interstellar visitors, analyze their composition, and understand their significance. We're reading messages from alien worlds. Not intelligent messages, necessarily, but messages nonetheless. Messages written in chemistry and physics and mathematics. Messages that are expanding our understanding of what's possible, what's common, what's rare in the universe, beyond our small corner of space. Now, let me take you even further into this connection between you and these cosmic wanderers, because there's something profound we need to discuss about timescales and perspective. You live, on average, about 80 years if you're lucky. In that span, you'll experience seasons, years, decades. You'll watch children grow up. You'll see technology change. You'll witness historical events. But from a cosmic perspective, 80 years is nothing. It's a blink, a fraction of a percent of Earth's history, let alone the universe's history. These twin comets have been in existence for millions of years, possibly hundreds of millions of years. They were old when the first humans evolved. They were ancient when dinosaurs walked the Earth. They've been wandering through the cold darkness of interstellar space, slowly tumbling, gradually changing as cosmic rays bombarded their surfaces and the faint radiation of distant stars warmed and cooled them in multi-million-year cycles. And now, for a brief moment in cosmic time, they're passing through our solar system. And you, with your 80-year lifespan, happen to be alive at exactly the right moment to know about it, to learn from it, to be changed by it. Think of it like this. Imagine you're standing on a beach, and a message in a bottle washes up at your feet. It was thrown into the ocean on the other side of the world, decades ago. The person who threw it is probably dead now, but the message is still intact, and you're the one who gets to read it. You're the one who gets to carry that knowledge forward. That's what we're experiencing with these interstellar objects. They're messages in bottles, thrown into the cosmic ocean millions of years ago by events we can barely imagine. And we're the ones who get to read them. We're the ones who get to understand what they're telling us about the galaxy we inhabit. But here's where it gets even more profound, and I need you to really think about this. If we can detect and study these objects, then other civilizations, if they exist, can do the same. When our sun eventually dies, not for another 5 billion years, So don't panic. It will enter a phase where it swells up into a red giant, potentially ejecting comets from our Oort cloud into interstellar space. Those comets will carry chemical signatures from our solar system. They'll contain organic compounds that formed on Earth or in the outer solar system. They might even contain traces of human-made materials if they pass through the region where our space probes are traveling. Billions of years from now, those comets might pass through another stellar system. And if there's an intelligent civilization there, they'll detect those comets. They'll analyze them. They'll wonder where they came from. They'll be having the same conversation we're having right now, but about objects from our world. We are all time travelers, in a sense. We're all sending messages to the future through the objects we create and the changes we make to our environment. And we're receiving messages from the past through objects like these twin comets. We're connected across vast spans of space and time through the simple fact that matter moves, changes, but persists. This is what I mean when I say these discoveries should change your worldview. It's not just about cool science facts. It's about recognizing that you are part of an ancient, ongoing conversation between different parts of the universe. You are both receiver and transmitter. You take in information from your environment, from your experiences, from discoveries like this, and you process it, integrate it, and pass it on to others and to the future. Your life matters not because of some cosmic grand plan, but because you are the universe's way of understanding itself in this particular time and place. No one else has your exact perspective, your exact combination of knowledge and experience and capability. You are unique in all the cosmos, and that makes you precious beyond measure. So when you look up at the night sky tonight, and you think about these twin comets racing through our solar system, I want you to feel a sense of kinship with them. They've survived unimaginable violence. They've endured millions of years in the frozen darkness. They've crossed distances so vast that light itself takes years to traverse them. And now they're here, briefly passing through our neighborhood, giving us a glimpse of their story. You might be going through your own challenges right now, your own versions of cosmic trauma, your own cold periods where you feel isolated and alone. And if you are, I want you to remember these comets. They kept going. They persisted. And eventually, they found themselves somewhere warm, somewhere bright, where their story could be witnessed and appreciated. Now, I know some of you are thinking, this is beautiful and poetic, but let's get back to the hard science. What are the actual implications of these discoveries for our understanding of planetary systems and comet formation? Fair enough. Let's go there, because what comes next is going to reorganize everything I've told you so far. Dr. Amaya Morrow-Martin at the Space Telescope Science Institute has been studying the population statistics of interstellar objects. She's trying to answer a fundamental question. How many rogue comets and asteroids are actually out there in the galaxy? And based on the detection rate we're seeing now, with improved telescopes, her calculations suggest something stunning. There might be more mass in rogue interstellar objects wandering between the stars than there is in all the planets, in all the stellar systems combined. Let me say that again, because it's so counterintuitive that your brain probably skipped right over it. The space between the stars might contain more planetary material than the space around the stars. Think of it like this. Imagine you're looking at a city from space. You see the buildings, the streets, the cars. That's like looking at stellar systems, concentrated, organized, visible. But what you don't see as easily is all the litter, all the debris, all the discarded objects scattered everywhere between the buildings. That's interstellar space. It's not empty. It's full of cosmic trash, cosmic refugees, cosmic wanderers. And the total mass of all that scattered material might exceed the total mass of all the organized systems. If that's true, and more data is needed to confirm it, then it fundamentally changes our understanding of galactic evolution. It means that stellar systems are far more dynamic and interactive than we thought. Material doesn't just stay put. It's constantly being exchanged, mixed, redistributed across vast distances. And here's where this connects to one of the deepest questions in science. How did life begin? We know that life on Earth requires certain building blocks: amino acids, nucleotides, lipids, sugars. We know that many of these compounds have been found in meteorites and comets from our own solar system. But what if Earth received a significant contribution of organic material from interstellar sources? What if the chemical recipe for life was partly written by comets from other stellar systems? Dr. Jennifer Bergner at UC Berkeley has been studying the organic chemistry of comets, trying to understand how complex organic molecules form in the cold, radiation-rich environment of space. In 2023, she published a groundbreaking paper showing that certain types of chemical reactions that don't happen efficiently in laboratory conditions on Earth can actually proceed quite readily in the icy surfaces of comets, catalyzed by cosmic rays and ultraviolet radiation from distant stars. She called it slow burn chemistry, reactions that take thousands or millions of years to complete, but which can produce remarkably complex molecules if given enough time. And interstellar comets, wandering through space for millions of years, have all the time in the world. The twin comets of 3I Atlas are giving us a chance to test these theories in real time. As they pass through our solar system, multiple research groups are studying their organic chemistry in unprecedented detail. They're looking for specific molecules, things like glycine, the simplest amino acid, or ribose, a sugar that's a key component of RNA. If they find these compounds, and if their isotopic signatures indicate they formed outside our solar system, it would be direct evidence that the building blocks of life can be transported between stellar systems. Let me be absolutely clear about what this would mean. It would suggest that life might not need to originate independently in every stellar system. The ingredients could be shared across vast distances, seeded from one system to another through the wandering of interstellar comets. This concept is called panspermia, and while it's been around for over a century, we've never had a way to test it properly. Until now. The twin comets are our test case. If their organic chemistry matches or exceeds the complexity we see in solar system comets, it tells us that the galaxy is well mixed, chemically speaking. If it's radically different, it tells us that different stellar environments produce different chemical possibilities, and life might have multiple independent origins across the galaxy. Either result is profound. Either result changes how we think about our place in the universe. Now, let me hit you with something that's going to seem like it's coming out of left field, but I promise it connects. These twin comets are teaching us about consciousness and perception. Stay with me here. One of the most fundamental questions in philosophy is whether reality is objective, whether it exists independent of observers, or whether observation itself plays a role in determining what's real. In quantum mechanics, this question becomes unavoidable, because particles genuinely seem to behave differently when they're being observed versus when they're not. But here's what these twin comets are teaching us. Observation matters at the macro scale too, just in a different way. Before 2024, these two objects existed in exactly the same way they exist now. They were following the same trajectories, exhibiting the same behaviors, carrying the same chemical signatures. But they weren't part of human knowledge. They weren't part of our story. They were, in a very real sense, invisible to our civilization. Then Cristobal Petrovich pointed his telescope at the right patch of sky at the right time, and suddenly they became real to us. They transitioned from unknown to known, from potential to actual, from background noise to signal. And the moment that happened, they changed us. They changed what we know about the universe. They changed the questions we ask. They changed the possibilities we can imagine. In being observed, they altered the observers. This is happening all the time, everywhere. Every act of observation is an interaction. Every measurement is a relationship. When you look at a star, Photons that left that star years or centuries ago are hitting your retina and triggering chemical reactions in your neurons. The star is reaching out, across space and time to touch you, literally. And in being touched, you're changed, even if only in the smallest way. The twin comets are teaching us that the universe isn't a collection of isolated objects. It's a network of interactions, a web of influences, a conversation between matter and energy unfolding across cosmic scales. And consciousness, your consciousness, human consciousness, is part of that conversation. You're not separate from the system you're observing. You're embedded in it. You're participating in it. This might sound abstract, but it has concrete implications for how we do science and how we live our lives. It means that the questions we choose to ask determine what we discover. It means that the tools we build shape what we can see. It means that every individual researcher, every student, every person watching this video and thinking about these ideas is actively participating in humanity's collective effort to understand the cosmos. You are not passive. You are not irrelevant. Your attention, your curiosity, your willingness to engage with difficult ideas, all of that matters. All of that contributes to the collective project of making sense of our existence. And these twin comets? They're inviting you into that project. They're asking you to think bigger, to question deeper, to wonder more intensely. They're asking you to look up at the night sky and recognize that you're looking at a dynamic living system that's constantly changing, constantly surprising us, constantly offering new mysteries to solve. Speaking of mysteries, let me tell you about something that happened just a few weeks ago that has astronomers absolutely baffled. In early February 2025, the James Webb Space Telescope turned its infrared eye toward the quiet twin, the one that's been showing sporadic outgassing. And what it saw has everyone scrambling to revise their models. The twin's nucleus, the solid body at the center, is not uniform in temperature. Different regions are at wildly different temperatures, varying by as much as 50 Kelvin, even though they're only kilometers apart. This shouldn't be possible for an object that's been in space for millions of years. It should have reached thermal equilibrium ages ago. The fact that it hasn't means there's some kind of internal heat source or some kind of insulation pattern that's far more complex than anything we've seen before. Dr. Naomi Rowe Gurney at NASA's Goddard Space Flight Center is leading the analysis of this data. Her preliminary findings suggest that the twin might have a layered structure, almost like an onion, with different layers having different thermal properties. When sunlight heats the surface, that heat doesn't penetrate uniformly. Instead, it gets channeled through certain pathways while being blocked by others, creating these temperature variations. But here's what's truly wild. The pattern of temperature variations seems to be changing as the comet rotates. It's not stable. It's dynamic. And that suggests that the internal structure is somehow responsive to heating, almost like it's actively regulating its own temperature. Now, before conspiracy theories start flying, let me be absolutely clear. There's no evidence of anything artificial here. What we're probably seeing is a natural consequence of how the comet broke apart and how different materials got mixed together during that process. But it's a natural consequence that we've never observed before. And it's teaching us that comets can be far more structurally complex than we realized. Think of it like this. We used to think of comets as simple objects, dirty snowballs, as I mentioned earlier. But these twin comets are showing us that they're more like geological bodies, with layers, structures, internal heat flows, and complex responses to external stimuli. They're not just chunks of ice and rock. They're worlds unto themselves, albeit tiny ones. And if that's true for these twins, it's probably true for many other comets too. We've just never had the opportunity to study an interstellar object in this much detail before. We're discovering that the universe is more intricate, more finely structured, more carefully put together than we gave it credit for. I want to zoom out for a moment and talk about the bigger picture, because we've covered a lot of ground, and I want to make sure you're seeing how all these pieces fit together. We started with the discovery of twin comets behaving weirdly. We explored their chemistry and found evidence they came from a different stellar system. We traced their trajectory and found they might have witnessed a supernova. We analyzed their structure and found they're more complex than we expected. And we discussed their organic content and realized they might be carrying the building blocks of life across interstellar distances. Every single one of these discoveries reinforces a central theme. The universe is interconnected. Nothing exists in isolation. Everything affects everything else, often in ways that aren't immediately obvious. These twin comets are physical manifestations of that interconnection. They're messengers linking different stellar systems, different epochs, different environments. They're proof that the galaxy isn't a collection of isolated islands, but a vast, churning sea where currents and waves carry material across unimaginable distances. And you, sitting there, watching this, thinking about these ideas, you're part of that same interconnected system. The atoms in your body have been on their own cosmic journey, recycled through multiple generations of stars before ending up in you. The photons hitting your eyes right now started their journey from your screen or your phone. But before that, they were electrical energy, and before that, they might have been chemical energy and fossil fuels formed from ancient organisms, which got their energy from the sun, which got its fuel from the gravitational collapse of a molecular cloud that was probably enriched with material from previous generations of stars. You are the current manifestation of a process that's been running for billions of years. You are a temporary pattern in the flow of matter and energy through space and time. And the fact that you, right now in this moment, can contemplate these twin comets racing through our solar system, the fact that you can understand their significance and feel a sense of wonder about them, that's one of the most remarkable things in the universe. Because consciousness is rare. As far as we know, it requires incredibly specific conditions. It requires a stable planet orbiting a stable star for billions of years. It requires the development of complex chemistry capable of self-replication and evolution. It requires the emergence of nervous systems capable of processing information about the environment. It requires, ultimately, the kind of brain you have in your head right now, about 3 pounds of tissue containing roughly 86 billion neurons forming trillions of connections. The odds against any particular consciousness existing are astronomical. The odds against your specific consciousness existing are literally incalculable. You are the result of an unbroken chain of causation stretching back to the Big Bang itself. And if any link in that chain had been even slightly different, you wouldn't be here. And yet, here you are, against all odds. A thinking, feeling being capable of understanding the universe that created you. And these twin comets are giving you something to think about, something to marvel at, something to integrate into your understanding of reality. That's not a small thing. That's precious. That's miraculous, even if it's a miracle that emerges from natural law rather than supernatural intervention. Now, let me take you to the absolute cutting edge of what we know about these twin comets, because there's been a development in the last few weeks that changes everything. And I mean everything. In late February 2025, an international team of researchers, led by Dr. Kat Volk at the University of Arizona, published a preprint paper, not yet peer-reviewed, but the data is solid, making a claim that seems impossible. They claim that the twin comets are in resonance with each other. Gravitational resonance. Here's what that means. When two objects orbit or move through space near each other, their gravitational fields can interact in ways that create stable, predictable patterns. Think of pushing someone on a swing. If you push at the right moment in each cycle, the swing goes higher and higher. That's resonance. The timing of your pushes matches the natural frequency of the swing. In the solar system, we see resonance everywhere. Many of Jupiter's moons are in resonance with each other. For every 3 orbits one moon makes, another makes exactly 2, for example. This isn't random. It's a consequence of how gravity works and how orbits naturally stabilize into these patterns. But finding resonance between two interstellar objects that just happen to be passing through our solar system? That should be impossible. There hasn't been enough time for their orbits to settle into a resonance. They're just passing through. They should be gravitationally independent. And yet, Dr. Volk's data shows a clear pattern. For every 2.3 rotations of the primary comet, the twin completes exactly 3 rotations. This ratio has held stable for the entire observation period. And when she ran the calculations backward, modeling their trajectories back into interstellar space, the resonance persists. These objects have been locked in this pattern for potentially millions of years. How is this possible? Dr. Volk proposes something radical. The twin comets never fully separated. They're still weakly bound by gravity, forming what's called a contact binary or a near-contact binary. They're not a single object anymore, but they're not fully independent either. There's something in between, held together by gravitational forces so subtle that it took months of precise measurements to detect them. If she's right, and again, this needs to be confirmed by other teams, then these aren't just twin comets. They're a binary system. A pair of objects dancing through space together, bound by forces that survived a supernova shockwave, millions of years of cosmic radiation, and the gravitational chaos of entering our solar system. Think about what that means. These two objects have been traveling together for longer than humans have existed. They've been partners in an endless waltz through the void, slowly tumbling around their common center of mass, never quite touching, but never quite separating either. There's something profoundly moving about that image. In a universe that's often described as cold, hostile, and indifferent, here are two objects that found each other, or stayed together, or refused to let go. They're survivors, but they're not alone. They have each other. I know I'm anthropomorphizing here. These are chunks of ice and rock, not sentient beings. They don't choose to stay together. It's just physics, just gravity, just the mathematical consequences of their masses and trajectories, and the initial conditions of their formation. But you know what? Sometimes physics is beautiful. Sometimes the mathematics of nature produces outcomes that feel meaningful, even if that meaning is something we're projecting onto them, rather than something inherent in them. And maybe that's okay. Maybe the human ability to find meaning, to see significance, to feel emotional connections to objects in space that we'll never know we exist. Maybe that's part of what makes consciousness valuable. We take a universe that operates on cold equations, and we warm it with our attention, our curiosity, our sense of wonder. These twin comets don't know they're teaching us anything. They don't know they're challenging our assumptions and expanding our understanding. They're just following the trajectory that physics dictates. But we know, we see, we understand. And in that understanding, we're transformed. Let me bring this back to something tangible, because I don't want to lose you in abstraction. What does all of this mean for the future? Where do we go from here? First, practically speaking, the astronomical community is now prioritizing the search for more interstellar objects. The Vera C. Rubin Observatory, which is scheduled to begin operations in 2025, will survey the entire visible sky every few nights, looking for anything that moves. It's expected to detect hundreds or thousands of interstellar visitors over its operational lifetime. That means we're about to enter an era where interstellar objects go from rare, exciting discoveries to routine observations that we can study systematically. We'll be able to characterize entire populations of these wanderers. We'll be able to understand which stellar environments produce which types of comets. We'll be able to trace material back to its sources and forward to its destinations. Within your lifetime, yes, yours, the person watching this, we will likely map out the chemical geography of our galactic neighborhood. We'll know which regions of space produce organic-rich comets, which regions produce icy bodies, which regions produce rocky asteroids, We'll understand the flows and patterns of material through the galaxy in ways that are currently impossible. And here's where it gets really exciting. Once we understand those patterns, we can use them to identify interesting targets for future space missions. We could potentially send probes to intercept interstellar objects as they pass through our solar system, not just observing them from Earth, but landing on them, drilling into them, directly sampling their composition. Imagine that. Imagine a spacecraft touching down on a comet from another stellar system. Imagine drilling through the layers and extracting a core sample that contains ice formed in the disk around a star that exploded millions of years ago. Imagine bringing that sample back to Earth and analyzing it in detail in a laboratory. That's not science fiction anymore. That's engineering and budget planning. Multiple space agencies are already discussing concepts for interstellar object intercept missions. The European Space Agency's Comet Interceptor mission, scheduled for launch in the late 2020s, is specifically designed to be flexible enough to target interstellar visitors, if any are detected during its operational lifetime. We are on the verge of directly sampling material from other stellar systems without having to travel light years to get it. The galaxy is delivering samples to our doorstep, and we're finally developing the technology to study them properly. But beyond the practical implications, there's something deeper happening here. These discoveries are changing how we see ourselves and our place in the cosmos. For most of human history, we've thought of our planet, our solar system, as separate and distinct from the rest of the universe. We're here. Everything else is out there. We observe it, we study it, but we're not really part of it. These interstellar objects are demolishing that worldview. They're physical proof that out there and here are connected. Material flows between stellar systems. Chemistry is shared across vast distances. We're not isolated. We're embedded in a galactic ecosystem, constantly exchanging material and energy with our cosmic neighborhood. And once you really internalize that, once you truly understand that you are made from atoms that have cycled through multiple stellar systems, that the water in your cells might have formed in a molecular cloud hundreds of light years away, that the calcium in your bones was synthesized in a supernova explosion that happened before Earth existed. Once you get that, really get it deep in your bones, it changes you. It makes your personal problems feel simultaneously smaller and more precious. Smaller because you realize that you're a tiny part of a vast, ancient process. More precious because you realize that despite being tiny, you're also unique, singular, unrepeatable. You are the only thing in the entire universe with your exact perspective, your exact combination of experiences and thoughts and capabilities. And it makes the problems facing humanity as a whole feel more urgent. Because we're the only known consciousness in this corner of the galaxy. We're the only beings who can understand these cosmic processes and appreciate their significance. If we destroy ourselves, if we fail to protect our planet and our civilization, we're not just losing human lives and human culture. We're extinguishing a light that might be extraordinarily rare in the universe. These twin comets have survived for millions of years. They've endured conditions that would annihilate us instantly. They've crossed distances we can barely imagine. And now they're here, sharing their story with us, teaching us about the galaxy we inhabit. Are we going to learn from them? Are we going to take this knowledge and use it to build a better, more thoughtful, more long-term oriented civilization? Are we going to recognize that we're part of something larger and act accordingly? I don't know the answer to that. Nobody does. The future is unwritten. But I do know this. Every person who learns about these discoveries, who thinks about their implications, who feels that sense of wonder and connection to the cosmos, every single one of those people is slightly more likely to make choices that acknowledge our cosmic context, to think bigger, to act with more wisdom, to care about the long-term survival and flourishing of consciousness in the universe. So by watching this, by sticking with me for this entire journey through the science and philosophy and implications of these twin comets, you've changed yourself. You're not the same person you were when you started watching. You know more. You understand more. You're more connected to the universe than you were before. And that matters. That ripples outward. You'll talk to people about this. You'll think about it when you look at the night sky. You'll make decisions, consciously or unconsciously, that are informed by this expanded perspective. And some of those decisions will affect other people, who will be affected in ways that affect still others, and the ripples spread outward through space and time. This is how culture changes. This is how civilization evolves. Not through grand proclamations or dramatic revolutions, but through millions of individual minds, one at a time, learning new things, making new connections, updating their worldviews, and acting accordingly. Let me close with one final mind-blowing revelation that ties everything together. Remember how I said these twin comets might have witnessed the death of their parent star? That they might be carrying the chemical signatures of a supernova explosion? Here's what I didn't tell you yet. Dr. Falzner's team, the ones who traced the trajectory backward, they didn't just identify the supernova remnant. They identified which specific supernova it was. About 3 million years ago, a star approximately 800 light-years from Earth exploded. We know this because we can see the expanding shell of gas and dust from that explosion. It's called Geminga, a name derived from the Milanese dialect meaning "it's not there," because when it was first discovered, astronomers could detect it with radio telescopes, but couldn't see it optically. It's now classified as a pulsar, a rapidly rotating neutron star, the collapsed core of the massive star that exploded. And according to Dr. Falzner's calculations, the trajectory of the twin comets, when traced back through 3 million years of galactic motion, passes directly through the Geminga supernova remnant at almost exactly the right time to have been hit by the blast wave. Do you understand what this means? These objects might be carrying direct physical samples of supernova ejecta. Their surfaces might be coated with iron, nickel, cobalt, and other heavy elements that were synthesized in the final moments before the star exploded. They might contain isotopes of elements that only exist because they were created in the extreme temperatures and pressures of a core collapse supernova. If we can send a mission to sample these comets, we could be directly analyzing supernova material. We could be answering questions about stellar nucleosynthesis, how elements are formed in dying stars that have been open for decades. We could be testing our models of supernova physics with real physical samples. This is one of the most extraordinary scientific opportunities in modern astronomy. And it's only possible because these two objects happened to pass through our solar system at exactly the right time, when we had exactly the right technology to detect and study them, and when a dedicated group of researchers happened to be paying attention. The universe has given us a gift, an incredible, precious gift. Two travelers from beyond our solar system, carrying stories written in chemistry and physics, asking us to read them, understand them, learn from them. Will we rise to the occasion? Will we fund the missions necessary to intercept these objects before they leave our solar system forever? Will we invest in the telescopes and instruments needed to find and study more interstellar visitors? Will we prioritize the long-term scientific exploration of our cosmic neighborhood? I hope so. I genuinely, deeply hope so. Because opportunities like this don't come along very often. These twin comets won't be in our solar system forever. In a few more years, they'll swing around the sun and head back out into interstellar space, potentially never to return. This is our chance, our moment. And if we let it slip away, we might not get another one in our lifetimes. So here's what I'm asking you to do. First, and most importantly, remember this feeling, this sense of wonder, this recognition of how extraordinary the universe is, this awareness of your place in the grand cosmic story. Hold on to that. Let it inform how you see the world and how you make decisions. Second, share this knowledge. Talk to people about these discoveries. Post about them. Write about them. Create art inspired by them. The more people who understand what's happening, the more support there will be for the science that makes these discoveries possible. Third, if you're in a position to influence funding decisions, whether that's through voting, advocacy, or direct participation in scientific institutions, support space science. Support astronomy. Support the missions and telescopes that let us study our universe. These discoveries don't happen automatically. They require sustained investment, dedicated researchers, and sophisticated technology. And they require a society that values knowledge for its own sake, not just for immediate practical applications. Finally, look up, literally. Go outside tonight, if the weather is clear, and look up at the stars. Think about what you've learned. Think about the twin comets racing through our solar system right now, visible in the night sky if you know where to look. Think about the vast distances they've traveled, the things they've witnessed, the stories they're telling us. And recognize that you're looking at a living, dynamic universe. Not a static backdrop, but an ever-changing system of matter and energy in constant motion, constant interaction, constant evolution. You're not separate from that system. You're part of it. You're made of it. You're the universe's way of knowing itself. These twin comets, 3I Atlas and its quieter sibling, they're messengers from a part of the universe we've never seen and never will see. Their parent star is dead, long gone, scattered into the interstellar medium. But these fragments remain, carrying memories encoded in chemistry, telling stories written in isotopes and organic molecules and strange thermal patterns. We are here now, in this brief moment of cosmic time, to receive their message, to understand it, to honor it by learning from it and passing that knowledge forward. And that, to me, is one of the most beautiful things about being human. We're temporary. We're fragile. We're confined to this one small planet orbiting an unremarkable star in an ordinary corner of an average galaxy. But we can think. We can understand. We can look at objects from beyond our solar system and decode their secrets. We can feel connected to processes that span millions of years and billions of kilometers. We are small, but we are mighty. We are brief, but we are significant. We are temporary patterns in the flow of matter through space and time, but we are patterns that can recognize ourselves, understand our context, and choose how to respond to what we learn. Choose wisdom. Choose curiosity. Choose wonder. Choose to be part of the ongoing conversation between consciousness and cosmos that these twin comets are inviting you into. Thank you for joining me on this journey. Thank you for caring enough to stick with this to the end. Thank you for being the kind of person who looks up at the universe and asks, what does this mean? How does this change how I see reality? How does this affect who I am and who I want to become? The twin comets of 3I Atlas are still out there, still moving, still carrying their precious cargo of information through our solar system. Their story isn't over. New discoveries are being made every week. By the time you watch this, there might be new findings that add to or modify what I've told you here. Stay curious. Keep learning. Keep looking up. The universe has more stories to tell, and you're here to listen to them. What an extraordinary privilege that is. What an extraordinary thing it is to be alive and conscious in a universe that can be understood. I'll see you in the comments. I want to hear what this made you think about, what questions it raised for you, how it changed your perspective. We're all in this together, this project of understanding our cosmic home. Your thoughts matter. Your questions matter. You matter. Until next time, keep wondering. Keep questioning. Keep looking at the universe with fresh eyes and an open mind. And remember, you are made of stars, and somewhere out there, new stars are being born from the material scattered by the ones that died. The cycle continues. The conversation goes on, and you're part of it.